Well, first of all, welcome and thanks all for joining my talk. So I have quite a bit of content. I have a lot of code samples, and I hope to do some live demos even. So yeah, so let's quickly get started. I would say if you have any questions, you can of course post them in the chat, and if time permits, I will try to answer them at the end of the talk. But I understood there's also a QA session going to be planned, so even if we don't have enough time to answer all your questions now, we can still do it at a later moment. So first, maybe a quick introduction of myself. Yeah, my name is Jeroen. I'm a consultant at Xibia, living in Amsterdam. My background is mostly Java and Scala programming. I'm also the founder, and I'm still running the Amsterdam Scala user group in Amsterdam. So if you're ever in Amsterdam, please come say hi. Yeah, of course, now with the whole situation, we have a bit of a stop of the meetups, but usually we have meetups every month. So yeah, you're very much welcome to join. Okay, so let's talk about bond trading. This is what my talk is focused around. Don't worry, I won't ask you for your banker's oath, so you won't need to be an expert in this domain, but there are a few things that you need to understand, like a few terms, to be able to follow this talk. So I made a little glossary. So what is a bond? Well, basically, it's a loan taken out by a company, and a company gets money from investors who buy the bond. So investors can basically bid on bonds. Bonds are identified by ISINs, which stands for International Securities Identification Number. And I'm going to use that later in the slides. Then there's another term, RFQ, which stands for Request for Quote. So it basically means you ask a financial institute, so it could be a bank, it could be like an insurance company or a government, for an offer on a bond. And then there's like bid and ask prices. So a bid price is the best potential price a buyer wants to transact at a certain moment, and the ask price is basically the best potential price a seller wants to transact at. So those are like a few terms that are the basics of the bond trading domain. Let's move on. So let's build an app, right? We want to provide some insights into the bond trading world. So we want to build like a tool that can do some analysis on this bond trading market. Well, the app is going to be very simple. We just want a few basic features. So first feature is we want to show the recent RFQs. Yeah, so we want basically a live view of RFQs coming in, and they should be enriched with some extra metadata. We'll talk about that a bit later. We also want to do some prediction. So we want to show like a predicted price for a bond, because we want to offer our buyers and our sellers like some insight in what they potentially should bid to actually be able to get the bond at the best possible price. And lastly, we want to also store some raw RFQ data in, let's say, Google BigQuery for some further analysis. So maybe our data scientists can pick this data, build some machine learning models out of it. So basically, what we're talking about here is kind of like a Lambda architecture, right? Where we have like both streaming data coming in. So we have a real-time processing pipeline, and we also have like maybe some batch process, right? Where our data scientist still needs to do some calculations, some further analysis, and at some point when they're ready, feed it back into the system, right? So how would some system like that look like? Well, as I mentioned, basically you have like two different layers. You have like a stream layer where you compute like a real-time view. well, tools that you could think of to use are like Spark streaming, Flink, Akka Streams. And on the other side, you have like a batch layer where you could also use Spark, of course, like the batch flavor of it. Do some pre-computing, right? In the end, at some point, also calculate a batch view, which you then serve for the end user to consume. So this is like the basic overview of what our app would look like. So let's talk about the data sources that we have. So we talked about RFQs, right? We want to have a live view. So we have a stream of RFQs coming in, and to make it easy, let's assume they come in over HTTP. Then we also have like a stream of bid-ask prices. They usually come in separately. Let's assume they also come over HTTP to make it simple. And then of course, right, this we're kind of like in the banking world, right? So we're in the enterprise world. So of course there's an FTP server somewhere. So let's say we have the metadata. So that belongs to the ISIN, so to the bond. We have that updated periodically at some FTP server, right? So we have like 3 different data sources to consume. So if we would draw this out in a component diagram, it would probably look like something like this. So on the left-hand side, we have a few data sources, right? We have the RFQs, we have the bid-ask prices, and we have the ISIN data. On the right-hand side, we then have our consumers, right? So we have our little application that's going to show the real-time views, and also it needs to get somehow the predictions. Let's say it gets it from like Firestore database. And then we have the raw data, right, going into BigQuery, and then we have some machine learning process in place. So maybe built on Jupyter and Spark, which our data scientists can go wild with and basically read from BigQuery, and when they're done, they're going to update some table in Firestore, so our app can use this. So this is like the basic overview. And in the middle, of course, this is our job, right? So we have to build this component to store, do some calculations, right? Store the results in Firestore and BigQuery, right? So, but let's split that out. So what does this stream processor all need to do? Basically, it needs to ingest data from the several sources, and there could be different protocols, right? In this case, we already talked about HTTP, but also FTP, right? Then it needs to combine data from those different streams. It needs to do some enrichment, right? So it might need to combine data coming from the FTP, so the ISIN data, with the matching RFQs that the RFQs for that particular bond. And it needs to basically stream the enriched RFQs to Firestore. It needs to stream the predictions to Firestore. And it also needs to stream the raw RFQ data to BigQuery. So as you can see, it's quite a bit of different tasks. It's really a lot for a single component. So you're dealing with different data streams that may or not be interconnected. So if you would design this application, you would probably handle those different streams in different stream processing components. You're not going to build like one big component that, and if you design those different stream processing components, they also might have different characteristics and different needs. So they might need to scale independently, right? Some components would be more memory intensive, right? They need a lot of resources in terms of RAM. Some components you might be able to run multiple instances in parallel, right? If it's if it's more like a computational problem. Also, you might need a different framework, right? That fits the job. So we already in the previous slide we already saw that there's different options, right? For stream processing alone, there's already many different frameworks out there. So there's Akka Streams, there's Flink, there's Spark, there's Kafka Streams. So and they all are slightly different, right? So maybe Flink fits a certain job better than Akka Streams, and vice versa. So, and also there might be different SLAs in place, right? So some components might be on the critical path, right? So let's say for our real-time view, it's pretty important that we always get the RFQs in our real-time view. Right? If we miss one, that's pretty crucial information to miss. But on the other hand, if we are losing some raw RFQ data in our BigQuery, it's not the end of the world. You could still base your prediction even if you don't have a complete overview of all the RFQs. So there's a difference in SLAs here between those components that handle that. Also, there might be a different release frequency, right? So some components have like a very changing roadmap, right? So you need to do many rolling updates because there's always new features to add or changes to make, and some are more like stable. Like if you wrote an exporter that writes raw RFQs to BigQuery, unless the RFQ model is rapidly going to change, which is quite unlikely, that implementation should be quite stable, right? So as you can see, there's quite a few different characteristics to deal with. So wouldn't it be great if it would be possible to have those components completely independent, so that we can fully tune them to our needs? That would be an ideal scenario. So this is where Cloudflow comes in. So Cloudflow is a toolkit, and it addresses exactly these needs. So it helps making sure that we can tick all those boxes that we just mentioned. So the scalability, the different frameworks of adding all those, of running our components in that way. So let's go over it. How does it look like? So what is Cloudflow in a nutshell? So it's basically a new toolkit from Lightbend to build distributed streaming applications. You can basically split your application in independent stream processing components, and they're called streamlets in Cloudflow terminology. So this is exactly what we need, right? This is exactly what we're talking about. And those streamlets, they can be connected to each other. So each streamlet has inlets and outlets, and that's the way basically they connect to each other. So data can flow between them. And you can define how streamlets connect to each other in what they call a pipeline definition. In Cloudflow terminology, it's called a blueprint of your application. I have examples of that a bit later, but this is basically the concept. So what Cloudflow does is it atomically deploys your streamlets individually as pods. So Cloudflow is aimed at Kubernetes. Of course, like it's 2020, right? So everything has to be on Kubernetes. But the streamlets they will be deployed as individual pods, but atomically. So Cloudflow understands that it's one application, but it's split out over multiple pods. And it ensures that data can flow between them through according to your pipeline definition, your blueprint. And it uses Kafka basically as a broker between the streamlets. So that's quite nice because you get a lot of stuff for free there. And basically they're built out of two simple concepts. So they have a shape what they call. They can have 0 or more inlets, and they can have 0 or more outlets. We're going to see examples of those later. And the second part is the logic, basically. So basically the business logic of what the streamlet needs to do. So it's very, very straightforward. So how would that look like in a deployed scenario? So as mentioned, they're deployed as pods to a Kubernetes cluster. So you can scale them individually, right? You can have, it has basically 3 replicas, and the same goes for the streamlet on the right-hand side. And in between, as mentioned, is Kafka, right? So they can send and receive data through Kafka. So one of the added benefits that you then get is that a streamlet, once it's successfully processed an element, it will basically commit an offset to Kafka. So it keeps track where it was in reading the data from Kafka. So the nice thing is, if, let's say, streamlet fails, your pod crashes, eventually it will be restarted by Kubernetes, right? That's one of the nice things it offers. And what happens then, once it's restarted, the streamlet reads the consumer offset from Kafka, so it knows where it left, basically, last time. So it starts from the next element after the last successful processed element. So you won't have any data loss. And this is all handled by the Cloudflow framework. As a developer, you almost don't have to do anything to achieve this. This is basically a core feature of Cloudflow. So it's quite nice. So let's look again at our list of requirements. And well, there's ingestion, right? There's some combining of data, enrichment, doing some prediction calculations, and then some exporting to either Firestore or BigQuery. And note that we can basically handle each of them in a separate streamlet, right? As mentioned, they might have different characteristics. So it's probably a good idea to separate those out. So if we look at our diagram again, we could basically split up this stream processing block that we had into a few separate streamlets. And I simplified it a bit for the purpose of this talk. So for simplicity, let's assume that the bid ask prices stream is already aggregated into the RFQ stream. So we're only talking about 2 sources here just to keep it simple. So we still have the RFQs, and bid ask prices are part of that already. And then we have, so the RFQs are coming from HTTP, and then we have the ISIN data coming from an FTP server. So an RFQ is always about a bond, remember? And a bond is identified by an ISIN. And for each ISIN, we have a bit of metadata in a message on an FTP. So then we basically have 2 different streamlets that are responsible for the ingress, right? We have one that's responsible for doing the ingress of the RFQs, one that is responsible for reading the ISIN metadata from the FTP. Then we have an enricher that is basically combining those 2 sources. We have like a predictor, which is basically using RFQ data to make some prediction. The output of both goes to Firestore exporter streamlet, which is basically writing those to Firestore tables. And then we have another stream, which is going from the RFQ ingress to the BigQuery exporter, which is basically writing to BigQuery. So yeah, well, that's quite a more structured view of our application. So Well, you saw on the previous slide, we have all those connections, right, between the streamlets. There's some data, there might be some data transformation happening in streamlets, and streamlets are connected to each other. So they're sending data to each other through Kafka, basically. So we need to tell Cloudflow how this data looks like. All right, there's no magic here. So there's a transformation happening when a streamlet reads a Kafka record into its own local data structure. There might be also a transformation happening when a streamlet writes back a result to a Kafka record for another streamlet to read. So there's a protocol in place here. And likewise, if we continue, another streamlet might do more transformations. So we need to define this protocol. We need to define this codec that is able to do those transformations, so the streamlets can basically talk to each other. Cloudflow uses the Afro format as the default codec, so that's quite convenient because you also get like some Afro features for free. So inlets and outlets both have an Afro codec by default. You can pick another type of codec, but in this case, I'm just going to stick with the default. So what does that mean? You need to represent your data model as Afro records. And then Cloudflow comes with an SVT plugin that can generate case classes based on the Afro schema you define. So that's really, really convenient. You have just one place where you just specify your format, and you don't have to worry about how that then is mapped to Scala classes. So how does such an Afro schema look like? Let's design one for the RFQ. So this is the basic structure. So there's a namespace, and this also will be the package name of your generated case class. So then there's a name that will be the name of the generated case class, as you might expect. And then there's a bunch of fields. And there's some, you can define fields for basic types, such as, in this case, a string or an integer. But you also can have like more complex types. So for instance, timestamps. Afro has this feature to define logical types. In this case, I can set it to timestamp millis. And then this automatically maps to a Java time instant. So that's quite convenient. Well, we're in the banking world, right? It's the trading domain, so precision is really important. So we cannot just use like simple floats. So we have to use big decimals here. So there's another logical type which has an automatic conversion to Scala math big decimal, and this is the decimal logical type. So you can set a precision and a scale, and basically then you can just work with big decimals in your code. So that's quite handy. And you can also do nesting, so you can embed records. So in this case, as I mentioned, since we already combined the bid ask prices within the RFQ objects, we're basically gonna embed the bid ask prices model, yeah, as a nested record on the RFQ type. All right, so let's look at now that we have the data model defined, we can actually start building our streamlets. So let's look at the overview again. Well, the first thing, let's start with the RFQ ingress. And luckily there's, so we need a server streamlet, and luckily there's already a default building block for that. So it's called the Akka server streamlet class. In this case, we don't have any inlets. This is basically an edge service, right? We're just getting, we're not reading data from Kafka. There's nothing yet. We need to get it into our system. So here we're just going to spin up an HTTP server, which is accepting some post or put requests to accept RFQs. So as I mentioned, Streamlit has a shape and a logic piece. So in this case, our shape is very simple. We have only one outlet. So we get through HTTP, we get RFQs in, and we write that back to Kafka. That's the only thing it should do. So also the logic in this case is very simple. We can use the built-in HTTP server logic, which is already automatically starting a server, serving on slash, basically very simple. And it accepts both post and put requests for RFQ objects. So of course, I'm not showing it on this slide, but you also would have to define your format for this. So if you're using JSON, you need probably something like spray JSON format defined, or if you're using XML, you need something else. So yeah, that's basic. This is basically the whole ingress. So single outlet, and in this case, we're writing to Kafka. So we can use a partitioning strategy to be able to, for instance, parallelize downstream streamlets, right? In this case, we're mapping by the instrument ID, because like for the enrichment, we want to make sure that all the RFQs for the same ISIN end up in the same partition. So they end up in the same consumer. So that's why in this case, we're partitioning by instrument ID. And then the next part, well, let's start with the raw flow, right? That should probably be the easiest. So now we just want to export them to BigQuery for further processing. So we create another streamlet, but in this case, we don't need a server, so we just pick the default Akka streamlet. And basically the main, so there's one inlet, the RFQs coming in that we just got into our system, and there's no outlet because again this is an edge service, so the output will be just stored in BigQuery and that's it. So there will be nothing written back to Kafka in this case. We just want to commit the offsets. So the basic logic is for an RFQ source, we want to convert each RFQ to a BigQuery record. We want to create a batch in it, of that, and then insert the whole batch into BigQuery. And then we just want to commit the offset to tell Kafka that we're done processing the records. So how does that look like? Cloudflow offers like a source with offset context. So it's basically an Akka Streams source, but with the, so for each element, you also get the offset. And this is what we need to be able to commit it back later. So we map that with some mapper function to a BigQuery record. Not going to show the code of that. It's not very interesting. And here, basically, you can use the same API as you would in a normal Akka Streams project. So you can do grouping, mapping, folding, and I'm basically folding all the records together to have like a batch insert object. And then I can also do async stuff, right? So here we can just asynchronously with some parallelism factor insert those batches into BigQuery. And then in the end, I just have to commit back the offsets. So once we have those two streamlets, we can basically hook them up. So this is where the blueprint comes in that I mentioned before. So each project has a blueprint file where you basically define which streamlets you have. In this case, I have two. Right? I have an RFQ ingress, and I have a BigQuery exporter. And then I have to define the connections between them. In this case, it's only one connection, so it's quite straightforward. We just say, okay, the outlet, which we called out for the RFQ ingress, is going to the inlet, which we called in, of the BigQuery exporter. And this is basically a valid application already. So we could potentially already ship this as a fully working application. But before that, it would be also nice to test it locally, right? Yeah. So basically, Cloudflow also offers like a sandbox environment built in. So you can run, so there's an SBT plugin, as I mentioned, and you can say run local. I hope this is visible for you guys. So what it now will do, it will basically read your blueprint file, determine which streamlets there are and which connections, and it will do some verification. So if you make a mistake here, like you have streamlets that are not connected to any that are not connected to anything, it's the same as in an Akka Streams graph, then it's invalid. So it would tell you. And also, if your data types don't match, because it knows that because of the Afro records, it would also tell you like, hey, this is an incompatible data type. If I would connect like an ISIN ingress to my RFQ BigQuery exporter, it won't work. So here, as you can see, we spun up a local HTTP server. So I can actually I can post some RFQs at this. So let's feed some stuff into the system. And well, the log file is here, but that's not the most interesting thing. So here we have a data set and we have an RFQ table created. I should have showed you before that it was empty, but when we query it now, we can see that basically data came in. So that already works. So that's quite cool. So we verified it locally before even deploying to Kubernetes, and move on with the next slide. So great. Let's extend our application. Right, the next step would be to add another data source, the ISIN data, which we're going to need for the enrichment step. And this is coming in from an FTP server. So we need to create another streamlet. And again, I pick Akka here. So it's going to be another Akka streamlet. It's again similar to the RFQ ingress. We have just a single outlet, but this time it's for ISINs. I'm also need to define an Afro schema, but I'm not going to show you this time because it's pretty much similar to what we've done before. Let's focus on the more interesting talk and implement this runnable graph again that we needed to do before. So what does it need to do? Every X minutes, it needs to list all the FTP files, it needs to parse the CSV for each file, and it needs to convert the parsed CSVs to ISINs, and then write each ISIN to the outlet sync. So, okay, how do we list from FTP? Well, if you were at Christoph's talk about the reactive manifesto this morning, you already heard about Alpaca. So the Alpaca project is really a super useful project in the Akka Streams world. It's basically a collection of libraries of reactive integration pipelines. It's built on top of Akka Streams, and it really makes it easy to integrate common APIs to an Akka Streams application. So there is the Alpaca FTP connector, which is quite useful. It basically has an ls function, which gives you a source of FTP files from an FTP. And there's a from path function, which you can use to read an FTP file. And you get like a source of byte strings. There's also a CSV parser, sorry. And this gives you flows. So you get a line scanner that gives you a flow of byte strings, and you have a CSV mapper, which can give you from a list of byte strings, so a list of lines. So a single line, I mean, it can give you a map, basically a dictionary with each field. So those functions are quite convenient to use, so we're going to use them. First of all, we need to do something every X minutes, right? So let's say every 20 minutes we want to read from this FTP. So we create a ticker. Then we're going to use the ls function. This gives us a list of files. So we want to flatten it out. We want to process each file separately. And then we need to parse this CSV. So I have here an imaginary function, read CSV from FTP, which is under the hood using the apakah CSV parser to do the magic. In this case, I don't really care about the order of how things are processed. So I'm going to use the slightly optimized map async unordered function. And then for each CSV that's coming in, and for each line of that, I'm going to convert that to an ISIN. And again, I'm going to flatten those results so that I get back an ISIN each time. And that result I'm going to write to our sync. And I'm going to use the plain sync here. I don't have to commit anything to Kafka because I'm not reading from Kafka. So I just want to write to Kafka. So that's basically what the ISIN ingress would look like. So now that we both have the RFQs and the ISIN data flowing through our system, we can actually build this enricher. And for this streamlet, so far we only used Akka Streams, but for this streamlet, we're better off using the Flink runtime. So this is again a benefit from Cloudflow. As I mentioned, sometimes a different framework just fits a little better. We have the freedom to do that. So in this case, I'm going to use Flink because this is basically joining of two different streams. So it involves stateful stream processing, right? We need to join on this instrument ID key, and we have no control over when matching elements will be available. So we need to keep state so we can match aggregated ISINs over time with new incoming RFQs and vice versa, right? We don't know which one comes in first. So let's look at the skeleton of a Flink streamlet. It's again pretty much the same, but in this case we have two inlets, one for ISINs and one for RFQs, and we have a single outlet with a different model, enriched RFQs. So this is our shape, two inlets, one outlet. And then the logic, we need to implement the Flink streamlet logic. So we need to implement our build execution graph function. What does it need to do? It needs to read the RFQ stream, key by instrument ID. It needs to read the ISIN stream, key by instrument ID again. It needs to connect the two streams, so join them, and apply the enrichment function. And then it needs to write the resulting enriched RFQ stream to the outlet. So it's pretty straightforward. So there's a read stream function, key by instrument ID. It's self-documenting code almost. This is the more interesting part. So you connect the RFQ stream to the ISIN stream. So they're going to be joined by key. And then you apply an enrichment function, which we're going to implement later. And the resulting enriched RFQ stream, we're going to write back to Kafka. So what does the enrichment function look like? Well, this is the skeleton. So it's a stateful function, as I mentioned. It needs to keep state for each match on the instrument ID. So there, in our model, a one-to-many relation between ISINs and RFQs. An RFQ belongs to one ISIN, but there can be many RFQs for one ISIN. In our state, we therefore need to keep a single ISIN and a list of RFQs until a matching ISIN comes in. So we have two flat map functions here, which we need to implement. One is called when an RFQ comes in, and the other is called when an ISIN comes in. So the first one, when an RFQ comes in, do we already have a matching ISIN? In that case, it's very simple. We call an enriched function and we write it back to our collector, which is going to write it back to the stream. If not, we need to aggregate this RFQ to our RFQ state, so our list of RFQs. When an ISIN comes in, we basically update the ISIN state. And then for each RFQ that we aggregated, we write the enriched object to our collector. And then since we've done that, we can clear the state because we already processed those RFQs, so we don't have to do that again. Well, this is this is basically all there's to it. So now we have our Enricher. Well, I'm not going to show you how to implement the Firestore exporter because that's like very similar to what we've done for the BigQuery exporter. There's just a different Google API you have to use. So leaving that out for now. We would have to extend our blueprint file, right? We have a few more streamlets we need to define, a few more connections to set up. And as you can see, our RFQ ingress is now writing to two different inlets, right? We were writing to the BigQuery exporter before, but now we're already also writing to the Enricher. So the last component for our app is the predictor. And also here, it makes sense to use Flink because we can benefit from the default windowing support. So this time we have a single inlet for RFQs and a single outlet for RFQ predictions. And again, we have to implement the build execution graph. So what do we need to build? Again, read the RFQ stream, key by instrument ID, and then we need to create some windows. In this case, we want to pick event time, because we want to know when the RFQ happened. And then we need to apply a prediction function to each window and write back the result. So this is very similar to what we've done before. Now we need to create windows. So in this case, if we assume that all timestamps are ascending, we can use the simple function, assign ascending timestamps, and we can just use the timestamp field that we defined on our RFQ. In other cases, you might need a different calculation. Let's keep it simple for now. Then we need to create sliding windows. So we pick a window size, we pick a slide, and we apply the window function. And then we need some aggregation, right? So we need to apply an aggregator to the events in our window. Well, that was basically what I wanted to show you. So conclusion of this talk. So what did we do? We assembled a stream application of independent stream processing components. And we saw that we could easily apply and mix different runtimes. So we could use Flink, might as well could have used Spark, and we used Akka. And we only had to focus on the business logic. That's basically the only part we needed to implement. Also, which I hope, if time permits, I could still show you in the demo, we didn't have to focus on operational burden of setting up our clusters, right? Flink requires a cluster, which you would normally need to set up. This is something that Cloudflow already does for you. It uses the Kubernetes operators to set up Kafka, to set up Flink, to set up Spark. So it really takes away all that pain. And components are deployed to K8s and individually scalable without a single line of YAML. So people that have worked with Kubernetes before know that it's basically you have to write a lot of YAML to get something done, even for deploying like simple Java applications. But here we didn't have to do that, right? So we only had to focus on our application, and Cloudflow makes sure that it can be deployed. And because we have Kafka under the hood, we don't have to be afraid of data loss. Okay, I will try to make it quick. So I have a Kubernetes cluster already set up. Cloudflow offers some scripts to do that, basically, and deploys basically the operators. So the only thing what I would have to do is I would run a command to build. And once I'm happy with my application, I would run this command, build and publish. So it will basically create one Docker image, which can be installed in Kubernetes. not going to show you that. I already prepared one before this talk. Let me copy that in. And then the Cloudflow also has a kubectl plugin, which you can run, which you can use to actually deploy your application, pass in some configuration. So in this case, it deployed my application. I can show it here, and here you can see all the different streamlets that it created. So it's still starting up. So I don't think we have enough time to show you everything, but at least here you can see that that everything is spinning up. We could use port forwarding again to feed it with RFQs. That is what I was about to show you, and then we could even see that Flink is picking up those messages and start crunching the numbers. Well, that's basically what I wanted to show you. Thank you.